Next topic is vectors. A vector is a quantity characterized by both magnitude and direction. It's represented by an arrow pointing in a specific direction with its length proportional to the magnitude of the vector. So magnitude is the size or length of a vector, often denoted with vertical absolute value brackets around the vector. The direction is the orientation or angle relative to a reference axis or another vector. Components. The vector can be expressed in terms of components along a coordinate axis. Let's take a look. Geometrically, vectors can be represented as arrows in space or as ordered n-tuples or column matrices. So here are a couple of vectors. The one in the upper right quadrant is 1, 1. The one in the bottom left quadrant is -1, -2. Of course, we can represent three-dimensional vectors as well. And after that, it obviously gets impossible to draw. So we rely solely on the column vectors. Now, given a vector v, we can multiply it by a scalar. Vectors work in much the same way as matrices. So multiplying a vector by a scalar c is done component-wise. Now, geometrically, if you're going to multiply a vector v by a scalar like 3, the size changes by a factor of 3. If you multiply a vector v by -1, you get a vector that's the same size but going in the opposite direction. Vector addition is component-wise, same way as for matrices. But geometrically, what we see is that vector addition is tip to tail. So if we want to add vector v to vector w, we simply move vector w to the tip of v, and we start at the tail of v to the tip of w, and we get v plus w. So if we want to add the vector 1, 2 to the vector 4, 6, we get 1 plus 4 is 5, 2 plus 6 is 8. Another thing we commonly do with vectors is take what's called a dot product. The dot product, u dot v, we take the first components, multiply them, take the second components, multiply them, etc., and then we add all of those things up. The dot product of 1, 2, 3 with 4, 5, 6 is 1 times 4, 2 times 5, 3 times 6, all added together to 32. Using the dot product, we can find the angle between two vectors. So cosine theta is equal to u dot v divided by the length of u times the length of v. And of course, cosine of theta is equal to 0 when theta is 90 degrees. So if that dot product, u dot v, is 0, then we know that our vectors have to be perpendicular, or what's called orthogonal. So if we take the dot product of 1, -1, 0 with 1, 1, 4, we get 1 times 1 plus 1 times -1 plus 0 times 4, which is 0, meaning that these two vectors are perpendicular or orthogonal to each other. This leads to the idea of a scalar projection and a vector projection. The scalar projection of A onto B is given by A dot B divided by the length of B. So the scalar projection of A onto B is the length of vector R in the picture. The vector projection of A onto B is the actual vector R, not just the length of R, and it's given by A dot B over length of B squared times vector B. So the scalar projection is a number indicating the length. The vector projection is an actual vector. So here we want to find the scalar and vector projections of vector A, 2, 3, 1, onto B, 5, negative 2, and 2. So the scalar projection of A onto B is A dot B divided by length of B. The length of B is 5 squared plus negative 2 squared plus 2 squared square root. So that's root 33. And A dot B is 5 times 2 plus 2 times negative 2 times 3 plus 2 times 1, which is 6. So the scalar projection is 6 over root 33. Now the vector projection is that scalar projection times B over the length of B. And so we end up with 6 over 33 times vector 5, negative 2, 2, or 2 over 11 times 5, negative 2, 2.